Okay, so for example 6, this one is actually pretty challenging. I know, it's going to be okay though. Because we don't have a function to manipulate, right? We're given terms, and it's all about understanding function notation and how to set up our models with Taylor polynomials. So it says a function f has derivatives of all orders at x equals 0. Okay, so just remember this is considered the center. So remember in our model for Taylor polynomials, it had like f prime of c and f of c and f double prime of c and x minus c. Your c is 0. Okay, so that's what this is telling us right here. Let the polynomial, Taylor polynomial, denote the nth degree for f about that center. So it is known that f of 0 equals -4, and that when we use the first degree Taylor polynomial to evaluate 1/2, it gives us -3. So using these two pieces of information, we're going to show that this has to be true. So in order for you to start this problem, you have to remember the general form of Taylor polynomials. So first, let's see if we can remember that. So if we're finding a first degree Taylor polynomial, okay, remember it's f of 0 plus f prime of 0, the first derivative over 1 factorial, times x minus that center to the first degree. So that's just the general form, and then we're going to actually plug in what we know. So we know that f of 0 equals -4. Okay, so I can go ahead and plug that in. And we're trying to prove this, so do not plug 2 in here because then you're assuming what you're being asked to prove. So we're simply going to leave that f prime of 0, and then x minus 0 to the first, of course, is just x. So this is your model. Okay, not your answer. This is your Taylor polynomial, and I should say first degree Taylor polynomial. So that's like your equation you're going to use. Now what they want you to do is use the fact that when you plug in 1/2, it gives you -3 to prove what that value has to be here. Okay, so basically I'm going to say then I know that the output is -3 when the input of x is 1/2. And then it's just a game of algebra, right? So I'm going to add 4 over, that's going to give me 1, and I'm going to write that as f prime of 0 over 2. And so this shows us that if we multiply both sides by 2, we can prove that's the value of f prime of 0. But you do not plug it in if that's what they're asking you to show. But that's all there is to that. Okay, so for part B, it is known that f double prime of 0 is -2/3, f triple prime of 0 is 1/3. Find the third degree Taylor polynomial. So again, let's just write the general term of it. And I know it's kind of annoying, but we're just going to try to create this habit so that we don't forget it. Because it's not hard, but if you don't do it enough, it will become a little more confusing. I am going to go ahead and just not write x minus 0 every time. Then the second derivative over 2 factorial times x squared, and then the third derivative over 3 factorial times x cubed. Okay, and then let's keep going from there. So I know from the part A that f of 0 is -4, and f prime of 0 was 2. Okay, and now we're going to plug in what we know. F double prime is -2/3. So that's going to become -2 over 3. And then I'm going to leave everything else with it. So 2 times 2 factorial here. And then I'm just going to say x squared to the side. Okay, and then f triple prime is 1/3. And that's going to be times 3 factorial, that was already there, and x cubed. And now we just simply clean it up. So -4 plus 2x, 2 factorial is just 2, so these basically just cancel out and leave you with negative 1/3 x squared. And here, that's really just going to be 3 times 6, so 1/18 x cubed. And that's it. So again, as long as you're familiar with the general form for any center, these are going to be pretty straightforward. All right, part C, the function h has first derivative given by h prime of x equals f of 2x. It's known that h of 0 equals 7. Find the third degree Taylor polynomial for h about the same center. So we need to make sure that's the case. What I would do first here is just try to process what they're telling me. They're telling me that the derivative of this function they're asking for is equal to f of 2x. So first I need to figure out what that looks like. So f of x is what we've been working with this whole time, right? It's what we just kind of wrote out right here. That's f of x, all right? So what we're going to do now is take this and do what we were practicing at the beginning of this lesson and substitute in that 2x piece. So everywhere there was an x, there's now a 2x in parentheses, and that's important since we have powers. And basically, let's kind of clean this up a bit. We're going to have that be negative 4 plus 4x. That's going to become 2 squared, or 4 over 3x squared. And then if I'm thinking ahead here, which you may or may not be at this point, if I'm going to be integrating these, because we're going from h prime to h, we're not really going to need this because that would give us the fourth term. But just for good measure, let's practice it anyways. That would give us 8 over 18, which is the same as 4 over 9 x cubed. Okay, so now if they want me to write the third degree Taylor polynomial for h about x equals 0, I'm going to be thinking of the integral, or of integrating what we just wrote out. Integrate. Okay, so that's going to become c, remember, not plus, minus 4x plus 2x squared. I'm just integrating each little piece here as we go. That would be what? Cubed. So that needs to be 9. And then I already have the third degree is represented, so we don't really need that guy. We have our degree of 3. So now I need to figure out what this constant is, and they give you an initial position of some type to use for that. So basically we know if we did 0 for the x's, we get 7 for c, so then that just means that 7 equals c. All very exciting. And so that's all we really have to do to get our final answer is fill in that value. But you do need to actually plug it in and double check that. Don't just always assume C will be the initial value, as was the case last year in AB Calc. All right, and that concludes your lesson.